Okay, hey everybody. Hello. Um, as ever, can I have a confirmation that I have a voice? Thank you. Okay, so we'll continue on what we did yesterday, and we'll try to finish all the sections that are in the syllabus. So the plan for today is to finish the change of variables, and then to start the vector calculus. We'll talk about vector fields and vector fields. And line integrals. Okay. Just a reminder that today there is a quiz. Don't forget this, please. Yeah, so what we did last time, just a reminder. Okay, so what we defined was, let me use the laser. So we wanted to, the rules, yeah, so there is no change in the rules, same concept. I think you have a certain amount of time to do it, and then the quiz will close. So yeah. So change of variables. We wanted to find a formula that is the same as this one in one dimension. And we started talking about transformations from the UV plane to the XY plane. So remember what we did? We started with a region R, and we wanted to find a region S such that when I apply the transformation to S, it gives me R. Yeah. Then a transformation is the image of a point UV is given by some function that depends on U and V, that's a two variable function, and then a two variable function on Y. And as I said, we'll assume that these functions, they are smooth and they're C1. Then we define that the image of a point is T of UV. And then you have to remember that all these transformations, they will actually be one-to-one. That's something you have to check, meaning that no 2 points will be sent to the same point. Then whenever I have this kind of transformation, I can define the pre-image, which means that I give you a point and you give me the point UV such that the image is x0, y0, and this is well defined if this does not happen. And then we did an example. I gave you a transformation just given by these functions here. And I told you to find the image of this square, or this rectangle. Then what we did is we see the boundary. We take the image of each boundary. So the image of this boundary S1 is the line U between 0 and 3, and V is 0. That's the S1. And then when I apply T to this segment here, I get, by the formula, X is 2U and Y is U. And then these are parameterized by U. So I want to find what they look like on the X, Y plane. So I need to get rid of U. When I get rid of U, I conclude that X is equal to 2Y and X is between 0 and 6. And this is just a line that is goes from 0 to 6 on the x-axis. And then I do the exact same thing on S2. I parameterize. U is now fixed and V is variable from 0 to 2. And then I take the image of this thing. I get something, I get X as a function of V, and then get U as a function of V. Then I want to look what they look like on the XY plane. So I have to get rid of V. So when I isolate, it gives me that X is equal to factor minus 3Y. And this is also a line. So this is TS2. And then I keep doing the same thing. This is T of S4. Okay. Okay, so now I'm just gonna give you the answer, or maybe, so yeah, the goal for the first hour is to finish the change of variables. So I'm just gonna give you the answer for TS3 and TS4. So TS4 is, no, I guess TS3. So wait a moment. Where is TS4? I did TS2. Oh, TS4 is this is TS3. So you're supposed to get X is equal to 2Y plus 10, and X is between 0 and 6. Right? And then for TS4, right? TS4. I'm not sure. I think I have a typo on my notes. TS3 or TS4, TS3 is V equal to 2. So this is TS4. 6 and 12. No, this is a typo. It's okay. Let me see. Okay. Sorry, you guys are laboratory mouses because this is the first version of my notes. So. Okay, TS4. Okay. TS3 is you're supposed to get x is equal to 2y plus 10, and x is between 6 and 12. And then for S4, you're supposed to get x is equal to 2y. Okay, I'm confused here. Something bad happens. Not the same thing. But I'll let you do TS4. It's not that hard. But you're supposed to get this. This is true. You're supposed to get this line because this is uh, meaning that y is equal to x minus 10 over 2. So it's a positive thing. So it's not TS4 either. Okay. I can do it, but it's gonna take some time. But maybe yeah. Um, hmm. mm, okay. 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 So maybe it's not the right diagram in the sense that yeah, it's not the right diagram here because when you get this line here, right? When you get this line here, it's x between 6. So it's between 3 and 1, right? When x is equal to 6, that is 6 plus 3, it's 9. 9 over 3, it's 3. So y is between 3. And when x is equal to 12, it's 3 over 3, which is 1. So it's not 0 here, it's 1. Okay? So please, just a little mistake here. So it's not really, 0 here, it's 1. Okay? And this is TS4. Okay? Right? Because y is between, because this one gives you y is between 3 and 1. right? Right. So when you do this S3, now it matches because when x is equal to 6, uh, it's -2, which is here, right? 6 minus 10 is 4, the -2. And then 12, which is 12 minus 10, it's 2 over 2, it's 1. This is -2. Yeah. Right? So they match. Okay, so now I'll let you do GS4 exercise. Right? I think I will just be careful because I have some typos on my notes and that is completely normal. So I will just remove the S4 because that's not the right answer. But you have the line, so I mean you can guess it. It's the line that goes from this point to 0. Minus like -2, like 6 minus 2 is the line that goes from -2 to 0, -6 minus 2 to 0. And you check that that's the right one. Let me just get rid of this on my notes. Okay. But it's not hard, you just have to do it slowly and carefully. Okay, is everything okay? If you have any questions, please don't hesitate. Okay. So now let's see how let's go back to the original goal, which is to see how the change of variables affects the integral. Okay. Let us now see how a change of variable affects the integral, a double integral. Okay. Okay. Now let's take a rectangle on the UV plane and then okay. Suppose I have a region R here. Okay, that's normal region XY plane. And then I have a transformation T, and I have a rectangle. Right? We're gonna start with the rectangle S. We'll see why. Suppose I have a rectangle, just as we did in this example. I have a rectangle, and when I apply T, it gives me some other region, depending on the transformation T. We'll call this U, V. We will call this is U0. This is V0, right? So this is the point U0, V0. Okay. We have delta V. And then we'll have delta U. It's the length of each side of the rectangle. Okay. Then suppose that when I apply t to the point u0, v0, I get the point x0, y0. Okay. Okay. Here, suppose that t of s is equal to r, and it's 1-to-1. But we're not going to use the fact that it's 1-to-1. It's a very technical thing. Okay. Suppose that t of s is x0, is r, and with x0, y0. So here, I would like you to follow me a bit carefully because because I will explain something, but you may want to add some notations to your notes because I don't want to pack the notations. You will understand what I'm saying, but I will write something, but make sure that you understand what I mean when I write it. It's not necessarily clear when I will write it. Okay, this is very abstract. I'm just gonna stop and let you know when I'm gonna do this. Okay, x0, y0 is t of u0, y0. Okay, and x is some function of u, v, and y is some function of h, it's some function h of u, v. Okay, all right. Now, the vector, now we're going to use a vector notation. The vector r uv given by guv I plus huv j, right? This is the vector r that depends on u and v, right? Gives the image of u, v. Okay, that's clear. Okay, so this point is just this point here. Now fix v equal to v0, right? So when you fix v equal to v0, as you're gonna go over this line, right? When you fix v is equal to v0, you're taking the image of this boundary. And the image of this boundary will be given by this line here, right? So when V0 is fixed, now the image of the lower side of S is a curve, right? Is a curve given by, is a curve R, U, V0. Is a curve parameterized by the parameter U, okay? So now you are familiar with curves, I suppose so. So the tangent vector at, so here you really need to follow me closely because we are really talking about point, the image of what? The image of the lower side. Oh, lower side. Of S. The lower side of S is a curve, right? This curve here, right? So now, what is the tangent vector at this point here? Tangent vector at this point here is RU. You know how to do this. It's del U of G when U is, right? So, okay, I'm gonna write this a bit careful, slowly here, but you're supposed to know this. See, so it's uh, del GU V0 Y plus del U H U V0 evaluated at the point U0 V0, and that is why I said you have to be careful if you want to add something that is going to help you, because I'm not going to write it all the way along, right? Because it's going to be really messy to add these lines and each time tell that this is evaluated at the point U0 V0, right? It's evaluated at the point U equal to 0, right? You see it's already messy, but make sure please to understand it. So it's equal to G U at the point U0 V0 I plus H U U0 V0 J. Okay, so here again comes what I said. This is equal to, so here's the book says this, all right? But you really want to understand what it means. So if you really want to follow the book, this is what it says, but make sure you understand that this is actually, I'm not going to write it all the way along. I'm just going to write it here. This is actually what it means is really del X, del U evaluated at the point U0, V0, Y, that del U, del evaluated at the point U0, V0, J, right? Because X is a function of U and V. So that's the tangent vector U at the point U0, V0. But again, I'm not gonna write this, right? I'm gonna write this all the way along. So, but we will understand what we mean. So this is actually the tangent vector here. And the same thing for V, right? Similarly for V, similarly for the tangent vector of the curve now we fix U0 and we go with V, right? Now U0 is fixed. U0 is fixed, and we go this way. So it'll give us another curve here, right? Of the curve U0 at x0, y0 is RV is GV U0 V0 Y plus HV U0 V0 J, and the same. But again, make sure you understand what this means. This is evaluated at the point U0 V0. Okay? Okay. So we are in the XY plane. And we have a region R. Let me do something. Okay. Okay. So because these transformations are very continuous transformations, right? When S is a very small rectangle, R is also is also very small. Okay? So the image of S will look like a parallelogram. Right? We're not going to justify this for parallelogram. I mean, of course, there is a way of doing this very in details with epsilon and deltas and all of that. But intuitively speaking, this is all what you are asked for. It looks like it's exactly the same thing as when you have a curve and you're very close to the curve, a line will look like a curve. That's exactly the same thing, but a bit more sophisticated, I would say, because we have like a transformation, it's a rectangle, but take it for granted. From an intuitive point of view, it makes sense. When S is very small, you're not moving that far from the point X, U0, V0, so you're really close. You're like, these are very small lines, and if the function is continuous, these lines will not be very distorted. So they will look like, each boundary will look like a very small line that is a little bit deformed, but it will still look like a line, okay? So take it for granted. Yeah, I mean, you can understand that it makes sense, right? So R looks like a parallelogram, right? So so when this is true, when S is very small, we can say that the rectangle R, the region R, is a little bit like the rectangle AB, right? here, remember, a rectangle is always given by two vectors, right? Okay. Of course, they're not going to be exactly the same on the other side, but uh, we can approximate R by the rectangle given by A and B, right? This is a rectangle, but it's not going to be exactly the same endpoints. But we can approximate. Okay, so what is A? Looks like a parallelogram, right? So we can approximate R by the parallelogram parallelogram no, parallelogram determined by A and B. But you will ask me, what is A and B? Well, these are the endpoints of the boundary. So you just do it. What is A? A is the vector R, the image of the point U0 plus delta U, V0 minus R, U0, V0. Okay, let me go back here and just take a screenshot and just so you can understand what I'm doing here. Okay, so I mean, this is the point. So we are fixing V0, right? And we're taking this point, will be mapped to this point here, right? This is the point R U0 plus U, right? So this is the point, right? And this is the point R of U0, right? So we are talking about this line here. Well, let me use the same color. We're talking about this line here, right? That this is A. And we do the same thing for the other, right? And okay, for B. Now B is given by R of U0, V0 plus delta U minus R at U0, V0, right? So again, this point is again, I hope it's not gonna be a mass spec. And this one is this point here. It's delta V, sorry. Delta V. And this point will be, oh, I hope this is helpful. I hope this is helpful and it's not confusing you. I really hope so. Okay, so, okay. So that's exactly what you're doing. Okay. However, recall that. Okay. However, recall that the tangent vector u Okay, okay. At the point u0, uh, the tangent vector are u at the point um, u0, v0, which is the tangent of the curve uh, of this curve, right? Is given by the limit when delta u goes to 0 of r u0 plus delta u v0 minus r of u0 v0 divided by delta u. This is just the definition of the tangent vector. We fix v0 and the tangent vector of the other side of the curve are v at the point u0 v0 is the limit when delta v goes to 0 of r u0 v0 plus delta v minus r u0 to v0 divided by delta v, right? So, so, so when delta u and delta v are very small, which means that the rectangle S is very small, it means that r of u0 plus delta u v0 minus r u0 v0 is approximately given by delta u times ru. Okay, so here, as I said, please make sure that you understand what I'm saying. I'm not gonna write this all the way along. Okay, because yeah, right. So this is exactly this. This is exactly the same thing as this one. And r of u0. Okay, I have an unstable internet. Is everything looks good? It says that I have an unstable internet. Can anyone confirm that everything is okay? Oh, thank you. Okay, so u0 plus delta v, thank you, minus r u0 is approximately given by delta v times rv. And again, I mean by that the same rv here. Because everything has to be evaluated at a point. Because it doesn't make sense to write ru. It's a function of u, right? But we don't want to keeping the right. This is gonna be really messy if we keep doing it everywhere. So that's why if you read the book, you can be confused. I don't know how if it confuses people or not, but I like to make sure that you understand that everything is evaluated at point u0 v0. So we are really looking at the point u0 v0. What happens here? We're looking really what happens here. So we have this formula here, right? But but remember that this is equal to, remember what is this equal to? Go back to A and B, right? A and B. These are exactly, this is exactly equal to A, and this is exactly equal to B. Right? From whatever. So the area of the rectangle, so the area of the rectangle R is approximately given by uh, the norm of the vector, A times B, which is the norm of the vector delta U RU cross delta V times RV, right? But again, this is all evaluated at the point U0, V0. Now, this is a number. It's a number. It's a scalar number, and this is a number. And then the properties of cross product, you know that if you have like scalars, you can take them out. So it's delta U, delta V, the norm of the vector RU cross RV. Okay. Okay. So what is our U times RV? We compute R U times RV. What is this? Well, you have to go back to in the beginning, right? It's a bit long, but you have to go back in the beginning, right? In the beginning, we gave you this. This is why I was doing this in the beginning. It's because I knew I will use it. Remember this? These two here? This is what we're gonna use right now. So you use them. And of course, they are on the UV plane, right? They are on the UV plane, they are in the XY plane. It's a bit you have to be careful. Everything is expressed as a function of UV, but remember that RU and RV are already evaluated at the point U0, V0. So these are actually two numbers, like it's two vectors, like two fixed numbers, two fixed vectors. They are already evaluated at the point U0, V0. So we are in the XY plane and we have a zero component along Z. So we have just compute del X, del U. So this is just what I said at the beginning. U 0, del X, del V, del Y, del V 0, right? Okay, so if you evaluate this thing here, it will give you del X, del, but remember, I'm gonna write this here. Again, in case you missed it, remember, warning. All of these partial derivatives are evaluated at U0, V0, okay? Del X, del U, del Y, del U, del X, del V, del Y, del V, K, right? Which is the same, this is the determinant of this matrix, which is the same thing as the determinant of this matrix here. I mean, compute this determinant here, right? It's gonna give you the same thing. Multiply this by this minus this. This is gonna same thing as this times this. Same thing. This times this minus this times this is the same thing as this entry times this entry minus this entry times this entry. It's the same thing. We just um, yeah. Okay, but why we did that is because this one has a very particular name. This is called the Jacobian of the transformation T, right? Notation. Uh, there are many notations, but the one the book is using is this one. It's Vx y del uv is the determinant of this matrix. Okay, oh, that's long, but we'll keep doing it. We're not done yet. We're not done yet. So back to the figure. We're still trying to find out the formula of the change of variable, but it's still. So the thing is, the Jacobian will play the, here's that kind of spoiler, but the Jacobian will actually play the role of the dx du when you have a one dimension change of variable. So let's see how this plays out. Okay, so back to our figure. We can write that the area of the rectangle, the area delta A of the rectangle R is, so here you really need to understand what you're doing. Okay, I'm gonna write it, I'm just gonna explain. I'm gonna write it here, but I will drop off this line next time. Evaluated times delta U delta V. Okay, so what I mean, what we did here, is this. Here's the conclusion. The conclusion is whenever you have a small rectangle, in the UV plane, and you apply a continuous transformation to this very small rectangle, and you get a very small region R that looks like a rectangle. The area of this rectangle R is the area of this small rectangle here, right? Okay, let me again use it here. It's a bit messy to start going back and forth. Okay, what we did here is this. Whenever you have a very small rectangle and the transformation that gives you another small region, the area of this rectangle, the curved rectangle, is the area of this rectangle, S, which is delta U delta V, times a number. And this number, what is this number is, take the Jacobian, take this determinant, compute it, evaluate at U0, V0. And so this is how much you are, when you change this rectangle, you will have to pick this factor here. It's not the same area. So this is how much you change the area of S when you apply T. But only applies, but remember, it only applies for small rectangles S, right? It's not always the truth, right? It's only if S is small. So how can you use this to do what we want? So, okay, so now we will go back to the real situation, which is I am giving you a region, right? I'm giving you a region R, okay, which is not necessarily small, and I have found a I have found a I found a okay, I have okay. I found sorry I wait, let me just do this. Keep the same. Um, I have a rectangle. I have a region R, and I have I have a let me just do this. Okay, so let's go back to this to the real situation where I have a region R in the XY plane, and I am in the UV plane, and I have my region S. Okay, that when I apply T, when I apply T, gives me R. Okay, these are not necessarily small regions, right? So what we do is, again, small rectangles. Small rectangles, we divide, we're not gonna be very precise here. We're just gonna divide this into small rectangles. And then we take one very small rectangle, we call it this one, right? We will call it Sij, okay? And the thing now is this one will be transformed into some small rectangles, right? And this one will be sent to some other rectangle. Call it R, I, J. And now because these are small, now we can use our formula. Now we can use our formula that says, so what is the integral? What is the integral over R of this function here in the dA? We are integrating over R. So again, remember that that's a bit tricky, but this is another division. I mean, we're not using exactly with the way we define the integral was very linear rectangles, and we took the limit. But again, you have to trust me that it's going to give you the same thing if you divide the region R into other curved rectangles. But, you know, so this is again, but the idea is the same. Take the small rectangles, small regions. It's the limit when n and m goes to infinity. But it doesn't necessarily mean that we are doing is not really math, or it's not really mathematically rigorous, because actually how people they did this in the beginning, how mathematicians they did these things in the beginning, in the 16th century and the 17th century, uh, uh, was actually this. They were not really rigorous. They had this kind of very generalistic arguments that we are doing here. And then people, 100 years or 200 years later, they give very formal proofs with all the details. But that is how we do math. We start with uh, very obvious things or intuitive things. I don't actually believe that. Some people, they say that intuitions doesn't really, is not good. Yes, but you need it. Okay, closing the bracket. This is exactly what we're doing here. We're taking the area of these rectangles, and then we're multiplying by the, you remember we had a star here, right? But here we're just picking some xi to be the corner here, to be the bottom left corner. This is the point xi, xj. Right? Remember that we had the freedom to choose the sample points inside the rectangle to be the center or the left corner or the upper left corner, whatever we want. But this one, we're going to choose this one because we want to apply our formula. Because remember, everything was done. This is actually the x0, y0. You remember, right? But now we have many x zeros and y zeros, so we're gonna label them by xi and the xj's, right? Because we want to apply the formula to each one of them. Okay, so we have xy and yj. Okay, so we have the rectangle R. Okay, now what is xi and yj? Remember, these were u0. These were x0 and y0 when we had this very small rectangle. So now we can change the variable. Can change the variable. Okay, so what is xi? What is yj? Is the image of some point, which is the image of this point here, ui vj. Okay, this is this image here. It's f of g ui vj, and what is yj? It's h u I vj, and now we apply our formula. What is the area of this rectangle? So we use this. We use this because now we have a very small rectangle. So what is the area? The area is the area of my small rectangle delta u delta v. Here, this is delta u, this is delta u, and this is delta v. But I have to pick up a factor, which is the Jacobian of the transformation, delta u delta v, evaluated at the point ui vg. Okay? Well, now I have a function, a new function, okay, that I am, and then I have this limit, and now the limit is, now everything is expressed as a function of u and v, and u and v are allowed to move inside this region S. So now that's actually the exact same thing as the integral This is exactly the same thing as the integral over the region S, because now I have delta U, delta V, right? Right? So, and what is the function that I'm integrating? Now it's another function, which is f of g uv at h of uv times this function here, which is the Jacobian. Okay? So that is, we're done. Whew, that was long, but we're done. This is what we wanted. This is the change of variable. And of course you have to, did I do this? Did I? Yeah, oh, all right, all right. Here we, uh, sorry, it's the absolute value, right? It's the absolute value of this. Sorry, you have to, can you please, because remember, we wanted the norm of this vector. So it's always positive, right? So it's the absolute value of this thing. Sorry about that. So it's the absolute value of this thing. So that's why the book doesn't use these lines to say, you see how messy it is, right? This is the absolute value of this thing. Okay, this is absolute value. Absolute value. Okay. Talking about the absolute value here. This is the norm, and this is the absolute value, means that something positive. Okay, so now this is not a formal proof, but the formal proof is a bit more complicated. So we have a theorem that says that suppose that T is C1 function, C1 transformation the Jacobian del x del y is not zero over S, T of S is equal to R, T is 1 to 1, okay, F is continuous, on R, okay, R is type 1 or type 2 region, okay, except here, except perhaps on the boundary, meaning that if you have a transformation that is not 1 to 1 on the boundary, it's still okay. Okay, then the following formula holds. And the formula is the integral over a region R of f x y dA is the same as the integral over S of f x, y. So if you change the variable, absolute value of the Jacobian, do we multiply the Jacobian at the end or inside the integral? It's inside the integral. We'll do an example, you'll see. Because the Jacobian is a function of, it's a function of u and v. This is, in general, this is a function, this, okay, so I'm gonna say remark. The Jacobian is a function of u and v, okay? So that's, so this is that's the formula. Okay, let us, so that's the formula you need to use. We'll do an example. We'll do an example. Okay, let me take a break. We'll be back at 11:30, I guess, or 33. Okay, so let me do an example of this and we'll move on to vector calculus. Example. And this is actually a familiar example. Okay, this is the region R. This is the angle beta. This is the angle alpha. And this is R equal to A. And this is R equal to B. And these are circles. Okay, these are small regions of a circle. Okay, so remember that was our rectangular polar. You remember the polar rectangle? That is exactly it. Okay, so now the idea is how can we integrate R? This is the X, Y, and we would like to find a transformation T such that we have a simpler region here in the UV plane. Okay. Now you will guess. So what now, to confuse you a little bit more, we're not going to use U and V. We're going to use R and theta. See, so that's very important to understand the concept, not just use formulas. So instead of UV, we're gonna use R theta. Okay. So take the transformation. So now, in general, you will need to find a transformation T and the region. I mean, you have two things to do. You have to choose. You have to find the region. You have to find the transformation and then the region. So here I'm gonna give it to you, but in a lot of cases it will be obvious from the integral you wanna evaluate. Take T of R theta to be R cos theta, R sine theta. You see? So these are very familiar ones. Remember, that was the this is the polar coordinates. This will be our x and y. Okay. So what is the Jacobian? This is dx, dr, dx, d theta, dy, dr, dy, d theta, which is the cos theta, r minus r sine theta, sine theta, r cos theta, which is r cos theta square plus r sine theta square, which is r. Now you have to check that this is okay. Now the region, you have to check the region. Now, when x, now the region will be given by, you have to check it, but when we are here, r is fixed and theta is allowed to move from alpha to beta, right? And same thing here, right? Theta is fixed and r moves from A to B. So if you check carefully, you will find that the region A is a rectangle that moves from A to B, right? So this is A to B. And then now theta is fixed and now R is fixed and we are on beta and this is B and this is A. So we are here. And then we move back when theta is fixed again. And then we move back again to the original point. And this is our rectangle and this is alpha and this is beta. And this is the region S. And you have to check that R, you have to check the theorem, right? Theorem says the Jacobian cannot vanish inside S. So we are done, we are okay because we are not hitting the origin here because this is where we're not hitting any R, something inside on the R line. So this is positive. Yeah, well, it's not equal to 0. And then you have to check the others, but it's going to take a long time. You have to check all of the three, but in general, these are obvious. These are obvious. Like type 1, type 2, you can break it down. And then you know, you can break it down into type 1 and type 2 region. And the one you need to choose, the one you need to really be careful with is the one-to-one. And TS equal to R, and the Jacobian is not 0. So here it maps S to R. It's obvious, you know, like boundary to the boundary and the inside with the inside. It's one-to-one. You have to check it, but not gonna do it. Just make sure that solve an equation of when 2 points give the same point, check that they are different, and that's it. Once you do that, then the integral over R of any function f x y dx dy is by the theorem says that it's the region, it's the integral from a to b, from alpha to beta of f of R cos theta R sine theta. Now we have to make sure that it's the absolute value of the Jacobian times dr d theta. And this is exactly equal to R, right? So this is what I told you, do not forget R. It's a Jacobian, right? You see, so these are two ways of proving this change of variable. So we have already done a change of variable actually without knowing it when we did the polar coordinates. So yeah, don't forget this R, it's a Jacobian. And it makes sense for a person who asked me, is it inside or the outside the integral? It's inside because it's R, it depends on R. So if you take it outside the integral, it's R. What is R? Okay, I think I will give you another example, but it's gonna be very quick. I'm sorry, because we still have 1 hour and 15 minutes, and we need to we really need to do the vector calculus. So another example would be this one. Evaluate. I'm just gonna give you the answer. Evaluate the integral R sine x plus 2y cos x minus 2y dA over the region over the region, this is 2 pi and this is pi. And we are on the y-x axis. So the idea here is you're not gonna be able to do it manually using x and y. It's not an easy function. So the idea is you need to change the variable. So change the variable, change of variables. So when I say it's obvious from the integral is because you have to try something and then see it's gonna work. So the one that's gonna work here is the obvious one. What are the what is something that's gonna work? I mean, it's gonna work if I have x plus 2y is equal to u, and that is the simplest way. And you have x minus 2y is equal to v. Okay, because if I have this and the Jacobian, now we have to check the Jacobian, and the Jacobian here, it's not gonna complicate the function because, well, first of all, you have to isolate x. So now isolate x and check that Jacobian is not gonna make your function harder because it's not gonna help. Isolate x and y, because this is how you're gonna get the transformation from the UV plane to the XY plane. Not this one is not the right one. So when you isolate x, it gives you x is equal to 1/2 u plus v, and y is equal to 1/4 1 over 4 u minus v, right? So when you take this and you compute the Jacobian dx dy, right? It's just the determinant of the matrix 1 over 2, 1 over 2, 1 over 4, minus 1 over 4. It will give you minus 1 over 4, which is never 0 anyway. It's not a function anyway. So Jacobian here is not even going to be a function of u and v. You can just take it out right now. So that's a good sign. Now, the other thing is, now you have to check the region, right? So this is the region R, right? And then you have to do the same exact thing. Take the boundary here when y is equal to 0, or when y is equal to y and x is equal to 0. Isolate uv. You have to do it backward, just as exact same thing as we did before, but on the other way around. Like, for example, for this line here, you have y. You have x is equal to, oh, sorry, this is x. And this is x. So here what you have x is equal to 0, x is equal to x, and y is equal to 0. Now you plug this one in here, and it gives you u is equal to something, and v is equal to something, and now x is between 0 and 2 pi, so you isolate x, and gives you a relation between u and v. And you do this for these three things here. It's really easy. You start log, and you just be careful. And if you do this, you will realize that the region you will have is a rectangle, is a triangle that look like this. This is x, this is y, this is 2 pi, this is pi, and this is 2 pi. This is minus 2 pi, and this is 2 pi. And this is u, and this is v. Right, so this is s, and this is r. Now make sure that transformation is 1 to 1. Everything is gonna work out. Okay. Now the integral over r of this function here sorry, I wish I can do it in more detail, but I have to cut it off somewhere because we need to move. S sine u cos v, and then as I said, it's not going to complicate the function. It's just a number. And now this is a type 1 region, which is equal to the integral from minus u to u 0, 2 pi, 1 over 4, the function sine u cos v du, dv du. Sorry, is it too fast? Did you get it, guys? Which is equal to, now we can do it, right? It's 1 over 2, the integral over u, the integral over v. Well, this is the integral from 0 to 2 pi of the function 1 minus cos 2u. You have to do it carefully, because then dv is going to give you sine evaluated between u and minus u. These are an odd function, so it's 2u and then 2/4, it's 1/2, sine u squared, right? And then you have to take the antiderivative of sine u squared, which is 1 minus cos 2. You have to do it. And this is gonna give you 1/4 u minus 1/2. Sorry, it's 1/4, not over 1. 1/4 u minus 1/2 sine 2u, 2 pi, and 0, which is 1/2 pi. Okay, so yeah, the change of variables, sometimes it is gonna be obvious from the integral, or you're gonna just tell you, use this change of variable to compute it. But in many cases, there are only a few cases where it's worth it. Okay, let us move now to vector calculus. Calculus. Okay, so we'll start with a vector field. Okay, so the thing is, if you are given a region in the plane, what is the region of S? This is the region S. This is x equal to y. This is u equal to v. This is u equal to minus v, right? It's 2 pi minus pi, right? Does it answer your question? What is the region of S? You mean the region S? The region S is given by this triangle here. All right. Okay, so the vector field. So what is a vector field? Well, the vector field is a very easy concept. Is we have the xy plane, and imagine a particle, or even though something on the gravitational field of the Earth, at each point there will be a force that is applied to this that is applied somewhere, have a magnetic field or something. So at each point there is a function, there is a force F that is applied, and this function, this force, it depends on where you are, right? If you are in the hemisphere, you're not gonna attract, or you're not, the magnitude of the gravitational field is not going to be the same thing as in the south hemisphere, or in the equator. So it's not going to be the same, right? Depends on the position where you are, right? So it's a function, it's a vector function that at each point x, y, it gives you a vector, right? So that's a vector field. Okay, right? So it's a function. So a vector field is a function that goes from R2 to R2. Well, not really R2, but in general, it only defined over region D, right? It's only the region D, right? From region D inside R2 to R2, right? So explicitly speaking, is a function f that goes from here. What is this function? It's f of xy. Well, it gives you some two variable function here plus q. Yeah. Right? Because at each point you will have a x component and y component, and this component here will depend on where you are, and this component here, I mean, even though you stay here, right, this component will also depend on where you are, and this dependent is not necessarily the same, right? But an example would be an example. An example would be f of xy is equal to minus y I plus xj, right? So right? So at each point there will be, for example, here on this is x, this is y. So when y is equal to 0, when y is equal to 0, it'll increase as you go further from x, and it's gonna be positive here, right? It's gonna be bigger and bigger. Here it's gonna be same thing, but smaller and smaller on the other direction, right? And the same thing goes from when x is 0. When x is 0 and y is positive, it's gonna be something like that. Like for example, 1 is gonna be minus 1. Vector minus 1, 0 minus 1. And same thing. It's gonna be lesser, lesser. And here it's gonna be bigger and bigger, right? And of course, if we choose another point here, let's say one, I don't know, 1, 2, 3, 4, 4, 4, 1, 2, 3, 4, 5, 6, and he's 6, then you're gonna have some vector that looks like this. This is the vector minus 6, 4, right? And the same thing, like a tornado, right? And then as you're gonna move away from the origin, it's gonna be bigger again, right? So actually this will be, if you look at this circles, they will be actually, sorry, they will be actually tangent to these circles. The reason why is this true is actually, indeed, fxy is tangent to the circle x squared plus y squared is equal x0, right? Radius to the circle of radius, to the circle of radius. Now, an easy way to check this is just to take the scalar product. In fact, take the scalar product of this with x, right? Well, we're having this. This is your, let me call it R. This is R, and this will be F. If you take the scalar product, this is y. This is minus y I plus x j scalar with xi plus yj. Okay. Which is equal to minus y x plus x y, which is equal to 0. Okay. Okay. There is the gradient of a vector field of gradient field. Given a function of two variables, we can produce a vector field called the gradient field. And we denote it by delta f. Like if I have if fx is such a function, then the gradient of f is, this is the vector field fx is the gradient of delta f, which is del x f at the point x0, y0, plus del y fx y. Of course, we suppose that these partial derivatives, they exist. Okay, so example, example, the gradient of f xy given by x squared plus 2y plus y squared is the gradient field 2x y plus 2y j. Okay, and if you plot this, it look like Okay, it looked like this, and this is a true. You have seen this before. The gradient is perpendicular to the level curve x squared plus y squared is equal to c. Okay. This is true in general. It's always perpendicular to the level curve of any function. It's just a particular function here. Okay. We say that a vector field is conservative if it is equal to the gradient of some scalar function fx, y. Okay? And f is called the potential for f. Okay? Well, all this terminology comes from physics. And I did my undergrad in physics, and all of this is really from physics. It's I mean, one of the good things about the gravitational field, and it makes the fact that if you go from a point to another point, and wherever, I mean, if you go from a point of the city to another point of the city, and the amount of energy is going to take you is the same, whatever the path you're going to take. It'll take longer, but it'll take longer, but the energy is the same. You have to give the same amount of energy to move from a point A to a point B, whatever the curve we're going to choose. That's actually true in the space, because that's not necessarily true in the city, because okay, of course in the city you have to take the road, and it's not only the gravitational field that is involved. It's also the friction. The friction, that what makes a pad cost you much gas than another one, because the friction is not conservative force. The friction on the road is not a conservative force. There's no right. You cannot find a function f such that the gradient of this function is going to give you the force that is applied to you by the that is applied against you when you move against the wind or the road. But for the field of the gravitational field, the one that is pushing you downward, that one does not really care about which path you're going to take. If you take a straight line or a curve, you're going to spend the same amount of energy to fight that field, to fight that force, right? Okay. But the friction and the wind, these are not conservative force. For example, this is one of the greatest things about the gravitational field, is because it's conservative, and it's actually responsible for a lot of phenomena that we see. For example, and the reason is really a mathematical reason. For example, why? Because the gravitational field, it looks like this. It's not really two-dimensional field, but it looks like this. It's x over some square root of this. Of course, you have to add z if you really want to be, but it's the same thing. It's just another variable. J, and the reason why is because you can find this if you take this function, if you take the gradient of this function, and if you take the gradient of this function, then it's going to give you exactly this, right? And that's actually the form of the gravitational field. The gravitational field is G m large M over R squared, right? And when you take the component and 10 times some U, right? When you take the component, it's gonna look like this. It's gonna look like this. That is the force that is applied to you. This is the mass of the Earth. This is your mass, and this is how much you. This is the amount of force is applied against you when you move. Okay, so this is a conservative field. Okay, so this is just to introduce you to. Okay, I'm gonna take a little break, but let me just start this new section here. It's to the line integral. All right, so now we're gonna really talk about line integrals. Okay, hopefully I'm gonna get this done today. Line integrals are actually well, line integrals are exactly the amount of energy you spend when a force is applied to you. That's exactly how physicists they quantize the amount of the energy you have to spend if some force is applied and you need to move an object from A to B, and you're applying a force F. So how much energy you spend? It's exactly a line integral. And why is the line integral? Is because that's the right thing to do. It's exactly, it's a line integral. This is what you have to take. And then if you really want to understand why, you have to take a class in physics. But here we just give you what it's a mathematical thing, but if you really want to know why, you have to take a class in physics. Okay. All right, everyone. Let me be back in 12:25. Yeah. Welcome back. Okay, so we'll continue with the line integrals. Cool. Okay, so let's imagine that you have a curve. C given by okay, and assume that C is smooth, which means that X prime is not 0 and are continuous. And is never 0, okay? Okay, so this is X and this is Y. And we have the timeline. Okay, this is the timeline, which gives you from A to B, which gives you at the time t, where is your particle or car? What is the word after I assume that C is smooth? Yeah, it's smooth. Yeah, so we have the timeline, and at each point it gives you the at each time actually it gives you where is your particle, tells you where is your particle. You should guess right now what we'll do. We'll divide this timeline into small amounts of intervals, right? And this is the time t I minus 1, and this is the time ti, and here we'll choose a random point ti star. Correspondingly, there will be the same division of the curve, right? All right, and then this will be pi minus 1, and this will be pi, and here we'll have the point pi star, which will be some xi star y ji star, or j star. Okay, so we divide we divide AB into n subintervals, and choose a sample point. We choose a point ti star inside ti minus 1 ti. Okay, we denote by delta S I, the sub arc corresponding, okay, to the sub arc. I'm gonna use another notation from the book, so be aware that I'm not using the same thing. So I'm gonna call this arc P I minus 1 pi. I'm gonna call this the arc. Okay, that's not a really usual. That is not a. You'll not find this anywhere. But the reason I'm doing this is not just because I like to draw, but because I do like to draw actually, but it's because to make because afterward we will like to use another notation for the line that goes from the point pi minus 1 to pi, right? And then if I use, I just don't want to confuse you, because we will have to use, we will need the line, because there is a difference between between the arc and the line, right? And you have to make a difference. So because we're not going to be using this like throughout the, the rest of the argument, I'm just going to use this very ugly notation. Okay. Suppose f is a function of two variables. Whose domain include C. So it means that it makes sense to evaluate f on the C. Then form the Riemann series, from the series, from the Riemann sum then form the Riemann sum f evaluated at the point xi star y I star times delta Si. Okay? Now, be careful that this is not really the Riemann sum that we introduced in the beginning of the class, because we had xi, yj, right? And here we are xi. Did I say xi or? Yeah. They're only labeled by one index, I. The Riemann sum. This is not the form of Riemann sum, not really a Riemann sum. This is indeed. It looks like a Riemann sum. Okay? If the limit exists, we call it the line integral of f along c, and we denote it by integral over c of the function f(xy) ds, and this is the limit. All right, this is cool, but we would like to, just as we did with the surface areas and the change of variables, we would like to have an explicit formula of this thing here. So again, we will need to focus on the delta SI. Okay. So you have the point P I minus 1, and you have the point P I, and now we have the line, right? Now we have the line, not the right? Now we can approximate we can approximate the arc P I by the line, by the segment Pi minus 1 Pi, right? Here we have xi, and here we have xi minus 1. Here we have yi, and here we have yi minus 1, right? At time ti minus 1, we have 2 points, and at time ti, we have 2 points. Now, what is, okay, so delta, this is delta x, and this is delta y. Okay, now, now because these functions are continuous and they are C1, now applying the mean value, you remember the mean value, the mean, no, not the mean, sorry, the mean value theorem, although the main value, the most important. The mean value theorem applied to the function xt. So what is xt? Xt is a function that we have the timeline, and we have the point ti minus 1, and we have the point ti, right? So at this point, we have this xi, right? And at this point, we have xi, right? And it's a function, right? A function. Apply to the function xt, on the interval t I minus 1 ti gives t star inside this interval such that delta xi is x prime ti star delta t, right? Remember that theorem that says that if you have a function ti minus 1 and ti, and this is xi and this is xi, and this is some point and this is another point, and you have a function that is continuous, then there is a point here such that the tangent, right? Remember that the tangent is exactly the same as this tangent here, which is delta x over delta t. Remember that? So this is the tangent prime at t star, and this point will be somewhere here, right? That's the theorem. Now same thing for y, same applied to yt gives t star star, not necessarily the same. It's the same interval, but not necessarily two functions that are different. T star star such that delta y I is equal to y prime star star I delta t. Okay, so we actually have an estimate for delta x and delta y, and so we can estimate, if you have an estimate for delta x and delta, if you have an estimate for this and an estimate for this, then you can have an estimate for this using the old friend Pythagoras. So the segment pi minus 1 pi, length of it, I'm using different notations, but the length of it is given by the delta x, but here it depends also on right? You can add a little bit, you can add a little xi here, and not necessarily the same. You can be the same all the way along, but not necessarily the same width. Because although here it's gonna be the same one, the timeline, I know it's not gonna be the same necessarily, because the timeline, you can choose the same, small amounts of increments on t, but when you evaluate, it's not gonna be necessarily the same amount of delta, the variation on the x when you evaluate. So it's not necessarily the same all along the indices I. So this is I squared plus delta y I squared. Now we have an estimate for this. Now, because these delta t's are the same, because this is our variable, this is our independent variable t. Now now they're the same on both of them. Now you can take it out, and then it's x prime star evaluated at the point x t star I plus y prime squared t star star I delta t, right? Okay, so now we have an estimate for this sum here, which is from y to n, f evaluated the point x, t star, y, t star, T star fx ti star y ti star times the length, which will be the square root of this thing, hold on, wait a moment, hold on. Yeah, yeah, because remember this T star was a random point, inside, right? Because theoretically speaking, you will have 2 points here that are of importance. You will have the first one and you will have the second one. And remember here, we took like a random point. It was a random point, whatever you want to choose. So you scroll up a bit. Yeah, here's fine. Here's fine. Okay, so we have the freedom to choose this ti star. It doesn't matter. You just have to be inside ti minus 1 ti. Well, we choose ti star. We could have chosen a ti star star, but it's the same thing. Because anyway, we're not going to do the full details. But the point is, choose a random point. Okay, t star plus y star prime t I star star delta t. Okay. Now, the thing is, let me just see. Yeah. So this is a one variable. Remember, this is not even a double sum. This is one. This is a one. This is a one-dimensional Riemann sum. The only catch is you don't have the same ti. This ti star star. If you had ti star star, it could have it could give a Riemann sum if you had ti star, right? Right? But because they are not equal, uh, because of this ti star star, it's not really a Riemann sum. It's not. This is not really sum. This is not a real Riemann sum, right? Because remember, the one-dimensional Riemann sum, you had to have some ti star, and then some evaluate whatever the function you have on that ti star star. I mean, this one makes sense. This one makes sense. This one makes sense. But then you are evaluating the same function on. It's not. This, it's not really. You are changing the point t throughout the function. So it's not really a Riemann sum. The good news is this is not a real Riemann sum. But when f x y x prime y prime when f x y, x prime t, y prime t are continuous, because they are really close. Like, the reason is because this interval ti, the reason that the intuitive reason is this one is because this one is very small, ti and ti star will be very, very close to each other. And when these three functions, they are continuous, we can use a trick using analysis to approximate this one with, we can just say that this one is equal to same. I mean, in general, you cannot just remove this one and say, okay, this one is equal to 2i's. I mean, everything has to be nice inside. The function has to move continuously, right? So that's why we really assume all of these are continuous, so that this one can be removed and replaced by ti star. And so the good news is that when this uh, uh, when we pass to the limit, the limit exists, and is equal to the limit when n goes to infinity of this thing. Which will be the line integral, oh, sorry, which will be the integral and is equal to the integral s. Again, here I'm saying two things. I'm saying that when these are continuous, these are equal to the limit of the normal real sum, and the normal real sum will give you the limit of this here. Okay. So I mean, what are we doing exactly here? Like from a visual point of view. Suppose you have x, you have y, you have z, and you have a function, and you have the curve. Okay, you have the curve c. Okay. And then the function will move, right? Sorry, it will move also, right? It's a two-dimensional surface, right? Right. It's a two-dimensional surface, but right. This is it's a two-dimensional surface. But when you restrict to this curve, what happens is you are taking a kind of fence. They call it fence, or this kind of section, but not. You remember we used to have, we cut it off by a plane X Y, but here not doing like you're not using a plane. You're using a kind of what would be the right thing to say it? You're using the curve and columns, and as you are moving with this your column or your pen or whatever you have, and you're like you're uh, you're going through the function z, and then under the curve you're gonna have on the surface, just under this curve, you're gonna have some curve or a fence or a curtain or something, call it whatever you want, but you get the idea that you will have this area here. You will have this area here uh, that that is covered by the curve. Okay, I don't know if it's clear or not, but is it clear? It's clear. Right? So this is like at each point on the curve there is an image on the surface. At each point there is an image on the. I don't know how to do it. Like for these points, I don't know how to do it, to be honest. Uh, okay. All right. So that's the curtain or the fence you have when you use a curve. And what you're doing actually, this one is the area of this region here, this vertical region. That's the area. If you really look at it carefully, we are doing exactly the same thing. We took a very small piece of the curve, and then we multiplied by a point inside this curve. We did exactly what we're doing with the rectangles. We took a point inside this here, and then we took the image, and then we took the little base here, multiplied by the height of the rectangle, and then we did this for all the curve. So when we did add all of this, it gave us the area of the fence. All right. Okay. So that's the area. So it's the area. Okay, but here, just as we were doing with the volume, uh, only if f is positive. Okay, so it's 1 o'clock. Okay, but we will still have some, but I think it's gonna be just a mess if I try to give you an example that is. No, it's 1 o'clock. I cannot go. Yeah. Here, this page here. Yeah, so I think I will try just to catch up the next time. All right. Okay. All right, everyone. So anyway, the quiz today, the quiz this week is not about this. Okay, so see you next week. Thank you so much. Thanks. Okay, so are we done? Is there any question, or you want me to go back to another page? No. Okay, so I will stop sharing the screen right now. And see no question, I will end the meeting. Bye-bye.